Hey everybody, hope you're doing well. Ready for another lesson for this week. We're going to start out with arc measure in circle graphs. So a circle graph, surprise, surprise, is a circle, and each part is a percent of a circle. So here's an example of a circle graph. Let's say people had to choose among three things. 40% of the people chose A, 50% chose B, and 10% chose C. Well, if I wanted to know what the arc measure was for each one of these parts, in order to go from the percent to arc measure, all I'm going to do is multiply the percent by 360. And the reason why we're using that number 360 is because remember from the last lesson, 360 degrees in any circle. So right here, 360 degrees times 50%. And remember, when you multiply with a percent, turn it into a decimal. So move that decimal point over twice. So 360 times 0.50, and that's going to be 180. And we know that 50% of a circle, or half a circle, is a semicircle, and a semicircle is 180 degrees. So that checks out. For the 10%, 360 degrees times 0.10, and that's going to be 36. For the 40%, 360 degrees times 0.40, and that's going to be 144. And if you add 144, 36, and 180, you get 360, all the degrees in a circle. Next, we're going to talk about something called arc length. So arc length, remember length is a distance. So we're not talking about the measure of the arc, we're talking about the distance. The arc measure is the same as the central angle measurement. But the distance is actually if you measured along the circle and you found that length. So how do we find that? We've got the following formula. The arc length is going to equal the angle, whatever the central angle is, divided by 360 times 2 pi r. And let's break this down. So first of all, 2 pi r or pi d, that's circumference. That's the distance around a circle entirely. That's the length. And the angle divided by 360 tells you what percent of the circle you're dealing with. So for example, let's say the angle measurement was 180 and we were dealing with half of a circle, semicircle. So we would do 180 over 360, which would be 50%, times whatever the circumference is. And this number is going to change depending on what the radius is. Let's take a look and see what this looks like in a problem. So with this circle right here, you can see that we have a central angle that's 75 degrees and the radius is 4 meters in length. So the way we set this up is the central angle divided by 360, and this is going to tell us what percent of the circle this is. And we're going to multiply this percent by the circumference, which is 2 times pi times radius, and our radius is 4 meters. So when I put this in my calculator, I'm going to type in 75 divided by 360 times 2 times, and I'm going to use 3.14 for pi, then times 4. And when I do this, I'm going to get 5.23333 bar notation. So I'm going to round this to the nearest hundredth, and I'm going to say this is 5.23. Remember, these units are meters, so that means our circumference is going to be measured in meters as well. I believe if you used a pi button in a calculator, you would get 5.24 if you rounded that. So here I have the same problem, except instead of having a radius of 4 meters, now I have a radius of 6 meters. So how does this change? Well, it's still the same percent of the circle, 75 over 360. It's just now the circumference is different. And when you multiply this together, you should get 7.8499. So let's round to the nearest hundredth and make it 7.85. And this is going to be meters. If you use pi instead of 3.14, I believe you get the same thing. So see the difference between these two? Here, when the radius is bigger, that means that this circle is a little bit bigger. And what do you know? The same percent of the circle, it's going to have a longer arc length. As the circumference increases, the arc length increases if it's the same percent. Okay, so let's take a look at this problem right here. I'm going to throw in 2 curveballs. Follow me with this. So first of all, let's say I want to find the arc length for FG. So I have 130 over 360, because 360 degrees in a circle, times 2 pi. Now my radius, if you're going to put 10 down here, it would be wrong. Take a look at EG. That's a diameter. So to go from diameter to radius, divide that by 2. So my radius is going to be 5. So when you do your multiplication here, you should get about 11.34 meters. And now let's find length EF. So if this is 130 degrees and I know this is a diameter, what's this going to be? If that's a semicircle, 180 minus 130, that makes this 50. And you end up with about 4.36 meters. Okay, so we're going to do one more calculation with this just to make sure that these numbers are right. If you add up this plus this, you get 15.7 meters exactly. So what's that mean? Well, these two parts make up half of a circle, a semicircle. So that means that 15.7 would be the length from E to G. In other words, half of the circumference would be 15.7. Let's find out what the length would be for EG. It should be the exact same as this, because if this is a half a circle, so is this. So EG is going to be 180 over 360, because it's a semicircle, times 2 times pi times 5. And when I multiply that, I get 15.7 exactly. So this totally checks. One last check on this one, just for fun. If I know that each semicircle is 15.7, then the entire circumference of the circle should be double this. In other words, if this is 15.7 and that's 15.7, the whole length around the circle is going to be 15.7 times 2, which is 31.4. Now, if I take 100%, 360 over 360 times 2 times pi times 5, or if I just take directly my circumference formula, circumference equals 2 pi r, I should get the same number if we did everything correctly. So I have 2 times pi times radius, which is 5. And when I multiply that in the calculator, I get 31.4. So with this problem right here, you can see how all these bits are related. Hopefully this makes sense to you. Good luck on the practice sheet. Ask me any questions you have, and good luck on the quiz.